Let's start way back, looking at the ancient origins. Where did this idea first pop up? Maybe starting with the early Greek thinkers.
Well, probably the earliest recorded inkling we have from ancient Greece comes from Anaximander. This was back in the 6th century BCE. He used the term apeiron. It means something like unbounded, indefinite, maybe even infinite. For him, it was this primordial, endless substance that everything came from, foundational stuff. Fast forward a couple of centuries, and you get Aristotle. He made a really important distinction. He talked about potential infinity versus actual infinity. Potential infinity was okay, like you can always count one higher. But actual infinity, a completed, existing infinite quantity, he thought that was impossible, led to paradoxes. And this view kind of fueled this long debate. Did the Hellenistic Greeks have a horror of the infinite? You see it in phrasing, like with Euclid around 300 BCE. Talking about prime numbers, he didn't say there's an infinity of them.
Right, how do you put it?
He said prime numbers are more than any assigned multitude of prime numbers. Very careful wording. That and how he handled his parallel postulate made some scholars think, yeah, they were philosophically uncomfortable with actual infinity. But others argue, Euclid's proof itself was a clever way around that supposed horror, so it's debated.
Okay, here's where it gets really mind-bending for me, Zeno's paradoxes. Let's talk about Achilles and the tortoise. It's famous for a reason. You've got Achilles, the summer-fast runner, giving a tortoise a head start. So Achilles runs to where the tortoise started. But in that time, the tortoise has moved on a bit. Then Achilles runs to that new spot. But again, the tortoise creeps forward. It seems like this repeats forever, right? The tortoise is always just a little bit ahead, so Achilles can never actually overtake him. How does that work?
It's a brilliant paradox. But Zeno wasn't really trying to prove something about infinity itself. He was an Eleatic philosopher, and he used these paradoxes to argue that our common sense understanding of motion was flawed, that motion itself might be an illusion. Bertrand Russell called Zeno's paradoxes immeasurably subtle and profound. They really hit on deep conceptual problems.
So how do we resolve it? Because Achilles obviously does overtake the tortoise in reality.
Right. The proper mathematical resolution took a remarkably long time, over 2,000 years. It wasn't until 1821 with Augustin Louis Cauchy. He provided a really solid, rigorous definition of a limit. And crucially, he proved the formula for the sum of an infinite geometric series, a plus x squared and so on. For certain values of x, that infinite sum actually adds up to a finite number, a divided by 1 minus x.
Ah, okay. So the infinite number of steps adds up to a finite time.
Exactly. Let's use the example. Say Achilles runs at 10 meters per second, the tortoise at 0.1 meters, and the tortoise gets a 100-meter head start. Achilles covers the first 100 meters in 10 seconds. Tortoise moves 1 meter. Achilles covers that 1 meter in 0.1 seconds. Tortoise moves 0.01 meters. Achilles covers the 0.01 meters in 0.01 seconds, and so on. If you sum up all those time intervals, 10 plus 0.1 plus 0.01 plus 0.01 and so on, using Cauchy's formula, it converges. The total time is 10, 1 on 0.01, which is about 10.10101 seconds. Boom! He overtakes the tortoise.
Wow. So it wasn't just solving a puzzle. It was about developing the mathematical tools like limits and series to handle infinity properly. That really changed things. Now, you mentioned debates in Greece. What about other ancient cultures? Was this idea explored elsewhere early on, like in India?
Absolutely, and it's a fascinating contrast. There's a Jain mathematical text, the Surya Prajnapti, dating from maybe the 4th or 3rd century BCE. It shows really sophisticated understanding of numbers. They classified numbers into 3 main sets: innumerable, innumerable, and infinite.
Okay, that sounds kind of intuitive.
But they went further. Each category was subdivided into 3 orders. So you had lowest, intermediate, and highest innumerable numbers. Then nearly innumerable, truly innumerable, and innumerably innumerable. And 4 infinite, nearly infinite, truly infinite, and infinitely infinite.
Whoa, so they were already thinking about different levels or types of infinity way back then.
It certainly seems so. A really nuanced view, suggesting not all infinities are the same, centuries before similar ideas were rigorously developed in Europe.
So we've got this ancient Greek reluctance, maybe, and this early Indian sophistication. How do we get from there to infinity being, well, everywhere in modern math? Let's jump ahead to 17th century Europe. That seems to be a key turning point.
It really was. That's when mathematicians started to systematically use infinite concepts, not just philosophize about them. John Wallis in 1655 was the first to use our familiar infinity symbol, the lemniscate. He used it into sectionibus conicis. He was quite clever, using it in area calculations by dividing regions into essentially infinitely thin strips. He also used et cetera, to denote infinite series.
And Newton and Leibniz, the calculus guys.
Right. Isaac Newton worked extensively with equations involving an infinite number of terms. That was crucial for calculus. And Gottfried Leibniz, he speculated about infinite numbers and infinitesimals, these incredibly small quantities. He called them ideal entities, sort of like useful fictions that behaved like numbers but weren't quite real in the everyday sense.
Okay, so the groundwork is being laid. But the really massive shift, the one that redefined infinity for good, that came later, right, with Georg Cantor in the late 19th century.
But absolutely. Cantor's work was revolutionary and intensely controversial at the time. He fundamentally enlarged the study of infinity by rigorously proving that infinite sets can have different sizes.
That's the part that still kind of blows my mind. How can one infinity be bigger than another?
His classic example is comparing the set of integers, 1, 2, 3, with the set of all points on a line segment, the real numbers. He showed the number of points on the line. Its cardinality is actually a larger infinity than the number of integers. And modern mathematics, which is mostly built on what's called Zermelo-Fraenkel set theory, actually includes an axiom of infinity. It's a fundamental assumption, basically saying infinite sets are guaranteed to exist mathematically. This allows us to treat infinite objects, study them, manipulate them, just like finite ones. It might sound abstract, but it underpins a surprising amount. Even Andrew Wiles's proof of Fermat's last theorem, which seems like it's just about whole numbers, implicitly relies on the existence of these really, really large infinite sets in the background.
That's incredible. So infinity isn't just a weird edge case. It's baked into the foundations. So if it's so fundamental, how does it actually show up in different areas of modern math? Let's start with calculus, where Newton and Leibniz got the ball rolling.
Right. In real analysis, the main use of the symbol Lagrange is to talk about unbounded limits. When we say x approaches infinity, it just means x gets larger and larger without any upper bound. It's not treated as a specific number in that context. It's also crucial for integrals. If you integrate a function and the result is sha, it tells you the area under the curve is infinite, unbounded. But sometimes you can integrate a function over an infinite range, say from minus infinity to plus infinity, and get a finite number, which means the total area is finite even though the region stretches forever.
Like the area under a bell curve?
Exactly. That's a perfect example. And similarly, for infinite series, summing up infinitely many terms, infinity helps us understand if the sum settles down to a finite value, converges, or if it just keeps growing indefinitely, diverges to infinity. Now, there are contexts where infinity is treated more like a number. In the extended real number system, you actually add 2 points, positive infinity and negative infinity, to the number line. And in complex analysis, things get even more elegant with the Riemann sphere.
Riemann sphere, remind me.
You take the entire complex plane, think of it as a flat sheet, and you add just 1 point, called the point at infinity. Mess. You can visualize this as wrapping the plane onto a sphere, with the North Pole representing that single point at infinity. This is incredibly useful because it lets you treat infinity as a value. For instance, dividing any non-zero complex number zi's by 0 can be defined as resulting in mess. It tidies up a lot of theorems about complex functions.
Okay, so adding a point at infinity simplifies things in complex numbers. Are there other systems with different kinds of infinity? You mentioned Cantor's different sizes, but anything else?
Yes, there's non-standard analysis. It's a different approach to calculus that actually brings back those infinitesimals Leibniz was thinking about. These are numbers that are infinitely small, closer to 0 than any standard real number, but not actually 0. In this system, infinitesimals have multiplicative inverses, and those inverses are infinite numbers, living in what's called a hyperreal field.
And these infinite numbers are different from Cantor's.
They are distinct in a different way. If h is a hyperreal infinite number, then 2h is a different infinite number, and h plus 1 is also a different infinite number. It's not about the size of the set in the Cantorian sense, but about distinct infinite magnitudes within this ordered field. It's a subtle but important difference in perspective.
Very subtle. Okay, let's circle back to set theory then, because that's where Cantor really made his mark on understanding the sizes of infinity.
Right. The key idea, championed by Richard Dedekind as well, was using one-to-one correspondence to compare set sizes. This overturns the old intuition, sometimes called Galileo's paradox, that the whole must be bigger than its part. In fact, a set is formally defined as Dedekind infinite if it can be put into a one-to-one correspondence with a proper subset of itself.
Like mapping even numbers to all natural numbers.
Exactly. Or think of a line segment. You can map just the left half of the segment to the entire segment point for point. They have the same size, the same cardinality, even though one is visibly part of the other.
Mind-bending.
Building on this, Cantor identified two main types of infinite numbers. There are ordinal numbers, which describe the order type of well-ordered sets. Think of them as extending counting beyond the finite first, second, third, up to the first infinite ordinal, omega, then O plus 1, O plus 2, and so on. And then there are cardinal numbers, which measure the sheer size or quantity of members in a set. The smallest infinite cardinal is Aleph null, which is the cardinality of the set of natural numbers. Sets with this cardinality are called countably infinite. If an infinite set is too big to be put in one-to-one correspondence with the natural numbers, it's called uncountable.
Okay, and this is where the continuum comes in. The set of all real numbers.
Precisely. Cantor's truly stunning result was proving that the set of real numbers, the continuum, is uncountable. Its cardinality, often denoted C, is strictly greater than Aleph null. He showed that C is equal to 2 raised to the power of Aleph null. 2 years. There are fundamentally more real numbers than natural numbers.
Which leads to the continuum hypothesis.
Right. The continuum hypothesis, CH asks, is there any infinite set whose cardinality lies strictly between that of the natural numbers and that of the real numbers, C? Cantor believed the answer was no, that C is the very next cardinal number after A, meaning C equals A. But the truly astonishing thing, proven later by Gödel and Cohen, is that the continuum hypothesis is independent of the standard axioms of set theory. Zermelo-Fraenkel with choice, ZFC.
Meaning you can't prove it true or false within that system.
Exactly. It's undecidable within ZFC. You can consistently assume it's true or consistently assume it's false and build valid mathematical universes either way.
Wow. Okay. And you mentioned cardinal arithmetic showing a line is the same number of points as a plane. How is that even possible? My intuition screams no.
Our intuition is definitely built on finite experience. But cardinal arithmetic reveals these deep truths about infinite sets. The number of points on an infinite line is the same as the number of points in any finite segment of that line. That's maybe easier to accept, but it's also equal to the number of points in a two-dimensional plane, a three-dimensional space, or any finite dimensional space. They all have cardinality C.
Is there any way to visualize that? It feels so wrong.
Visualization is tricky, but think about the tangent function in trigonometry. It maps a finite interval, like a 1-to-1, onto the entire infinite real number line. That's one example of stretching a finite bit to cover an infinite one. Even more strikingly, Giuseppe Peano discovered space-filling curves in 1890. These are continuous curves that literally twist and turn so intricately that they pass through every single point in a two-dimensional square, or even a three-dimensional cube.
A one-dimensional line filling a two-dimensional square.
Yep. It establishes a one-to-one correspondence between the points on a line segment and the points in the square. It shows just how different cardinality is from our usual geometric notions of dimension and size when dealing with infinity.
This must have radically changed geometry itself then, because geometry always felt very finite, very concrete.
It did change the perspective. Traditionally, yeah, geometry dealt with lines as things you could extend indefinitely, not as things composed of infinitely many points. Points were just locations. But modern math, heavily influenced by set theory, now generally considers a line to be the set of its points, and that set is infinite.
Were there any exceptions earlier on?
Projective geometry was a notable one. It explicitly added points at infinity to Euclidean space. This was partly motivated by perspective in arc-parallel lines appearing to meet at a vanishing point on the horizon. Mathematically, it simplified things, ensuring any two lines in a projective plane always intersect at exactly one point. And of course, infinity pops up elsewhere. In functional analysis, you study vector spaces with infinite dimensions. And fractals. Think of the Koch snowflake. You keep adding triangles infinitely. The perimeter becomes infinitely long, but the area it encloses remains finite.
Amazing complexity from simple rules repeated infinitely. But surely not everyone was thrilled with this explosion of infinities. Didn't some mathematicians push back?
Oh, definitely. Leopold Kronecker was a major figure in the late 19th century who was deeply skeptical. His famous quote is, "God made the integers, all else is the work of man." He championed finitism. That's the philosophical stance that mathematical objects should only be considered legitimate if they can be constructed from natural numbers in a finite number of steps. Finitists reject the notion of actual completed infinities.
Interesting to see that resistance. Okay, let's broaden the scope now. We've seen infinity inside math, but how does it connect to the real world, to the physical universe?
That's one of the biggest questions in physics and cosmology. Is the universe itself spatially infinite? People have wondered for centuries. Thomas Digges in 1576, then Giordano Bruno in 1584, they both proposed infinite universes filled with countless stars and worlds. Bruno was famously burned at the stake, partly for these kinds of ideas.
Risky stuff back then. What does modern science say?
Modern cosmology looks for clues in the geometry of space-time. We can measure the curvature of the universe by looking at the cosmic microwave background radiation, the leftover heat from the Big Bang. Instruments like the WMA Peacecraft have made incredibly precise measurements. So far, the data is consistent with the universe being spatially flat on large scales.
And flat means infinite.
Not necessarily, and this is where it gets tricky. A flat geometry is consistent with an infinite universe, like an infinitely large flat sheet of paper. But you can also have a universe that is finite, yet still geometrically flat.
Wait, how? That sounds like a contradiction. Finite but flat.
Think about old video games, like Asteroids or Pac-Man. When you fly off one edge of the screen, you reappear on the opposite edge.
Right. The screen wraps around.
Exactly. The geometry on the screen is flat, Euclidean, but the overall topology is finite. It's like the surface of a torus or a donut. So our three-dimensional space could, in principle, be like that, finite in volume, but without any edge or boundary, and still perfectly flat locally. If you traveled far enough in one direction, you might eventually loop back to where you started.
Mind blown. Again.
And then you have other cosmological ideas involving infinity. The multiverse hypothesis suggests there could be an infinite number of parallel universes, maybe with different physical laws. Michio Kaku is a big proponent of exploring these ideas. Or cyclic models where the universe goes through infinite cycles of big bangs and big crunches or big bounces.
So infinity might be woven into the very fabric of reality or realities. What about other fields? Logic, computing.
In logic, there's the concept of an infinite regress argument. This is used to criticize a theory or justification if it leads to an endless chain of reasoning where one isn't expected or plausible. Like if explaining A requires B, explaining B requires C, and so on forever without reaching a foundational point.
Okay, a flaw in reasoning and computing.
In computing, infinity is surprisingly practical. The standard way computers handle floating point numbers, i.e. E754, actually includes specific representations for positive and negative infinity. These values can result from things like dividing by zero or numbers getting too large, overflow.
So the computer doesn't just crash.
Nope, it can produce an infinity value, and calculations can continue using it according to defined rules. Some programming languages like Java even let you use infinity directly as a constant. It can be useful, for example, as a starting value in algorithms looking for a minimum or maximum a sentinel value. And of course, every programmer dreads the accidental infinite loop, a piece of code that just runs forever because its exit condition is never met.
Huh, yes. Been there. Okay, finally, what about the more human side? Arts, games, even just how we think about this massive concept.
Well, in art, perspective drawing is all about infinity in a way. Those vanishing points on the horizon, they represent mathematical points at infinity. They allow artists to create realistic illusions of depth and distance on a flat canvas. M.C. Escher's work is famous for playing with infinity, endless staircases, repeating patterns that seem to go on forever, tessellations.
His stuff is amazing.
Definitely. In games, people have invented variations like infinite chess, played on a conceptually unbounded board. And in cognitive science, some linguists and philosophers, like George Lakoff, argue that our concept of infinity isn't fundamental, but is actually a metaphor. He calls it the basic metaphor of infinity, BMI. It's based on mentally projecting the endless process of counting, 1, 2, 3, and just imagining that sequence going on forever without end. It's how our finite minds try to grasp the infinite.
So we've journeyed from ancient Greece and India, through paradoxes and calculus, into the bizarre world of different-sized infinities, out to the cosmos, and back to our own minds and art. Infinity really does seem to transcend any single definition. It's evolved from philosophy to math, shaping physics, tech, and art along the way.
Yeah, it's quite a story. We saw how concepts that seemed like impossible paradoxes, like Zeno's, became solvable once we developed the right mathematical language limits, series, set theory, and the idea that there are different sizes of infinity. That just completely changed the game for understanding sets, numbers, the continuum. It really speaks to human curiosity and the power of abstract thought.